Hello everybody, my name is Matthias Bartelmann and I'm happy to give this plenary talk on kinetic field theory applied to cosmic structure formation. I would like to begin by thanking the organizers of this conference for making this event possible, and I'm grateful for the opportunity to give this talk about applications of kinetic field theory. I don't think that I will have to give much of a motivation for why we want to understand cosmic structure formation with analytic means. First of all, we want to see how we can connect the initial state of cosmic structures that you see illustrated here with the temperature fluctuations in the cosmic microwave background with the final state, for which I use this image of the galaxy distribution in the 2 mass, the 2 micron all skies away. We see the initial conditions here for cosmic structures. We see their final state, and we wish to understand by analytic means how the initial state develops into the final state. And of course, there are sophisticated numerical simulations which tell us how the initial state can transform into the final state. But analytic means have the advantage, first of all, that they can be generalized and adapted to other conditions than used in the numerical simulations. And the analytic techniques or analytic methods can tell us about the reasons for why cosmic structures develop as they do. One of the main reasons why we want to understand cosmic structure formation from fundamental principles is that, for example, gravitationally bound structures in the universe, such as this galaxy cluster, Abell 2261, develop not only in numerical simulations, but also in reality. A density profile, which is nearly or fully universal. And we see this NFW-shaped density profile, which is marked here as a blue line. And we wish to understand why universality like this characterizes cosmic structures. So now I would like to structure my talk into 2 essential pieces. In the first piece, I will develop the main ideas of kinetic field theory on the board. And in the second in the second part of my talk, I will then describe applications and results that we have achieved so far by applying kinetic field theory to different problems. So let me go now to the board and describe what I will call kinetic field theory in 6 steps. So KFT for kinetic field theory in 6 steps. I hope you can read my handwriting here. All right, so the first step has to do with particle trajectories. And the main idea of KFT is that we dissolve the density field of cosmic structures into particles whose physical state is given by a point x in phase space. And we study the phase space distribution of the particles at an initial time where the positions q and the momenta p get a superscript I. So then we have the physical state xi of a given particle at the initial slice through extended phase space. Here is time, and then the trajectory of this particular particle evolves away from this initial state along a trajectory that we denote by x bar of t. The main reason why we are doing this, why we dissolve the density field into particles, is that trajectories in phase space do not cross. And therefore, we build KFT on a description that by construction avoids the shell crossing problem. Now, the trajectory x bar of t is a solution of the Hamiltonian equation of motion, which I write as x dot equals the symplectic matrix I times the derivative of the Hamiltonian function with respect to the phase space coordinates x. Let me see if you can still see this. Yes, okay. All right, the symplectic matrix is given by this object here, and the Hamiltonian function, as usual, is the kinetic part, p squared over 2m plus an interaction potential phi. And we write this as the free Hamiltonian H0 plus the interaction Hamiltonian Hi. Now, of course, we have to port the Hamiltonian equations to an expanding background, which means that the particle mass m here becomes time dependent as we transform to Coulomb coordinates. But this will not concern us to a large degree. All right, so this means we can write the Hamiltonian equations as x dot minus dp h0 0 equals 0 minus dq hi. This is just one way of rewriting the Hamiltonian equations that are given above here. And I write them now in such a way that I have three Hamiltonian equations on the left side, which I solve by a Green's function of t and t prime. And I use the right-hand side as an inhomogeneity of these equations. And this means that I can write the trajectory of the particle through phase space as the Green's function of t and 0 times the initial state. This is the free motion of the particle. And minus the integral over all forces acting on the particle. So that's the integral from 0 to t over dt prime times the Green's function of t and t prime. And now I'm going to write the inhomogeneity as gradient of the interaction potential, which is to be taken at time t prime, and the gradient now acts on the configuration space only and not on phase space. So in this way we can construct the trajectories of the particles through phase space, and this has already been part one of, or the step one of the description of KFT in 6 steps. Now let me come to the second step. And the second step has to do with the Green's function. The Green's function has to transport the phase space position in time. So the Green's function of t and t prime is a matrix. It's a 6-component matrix, and I write this as 3 by 3, as a block matrix of 3 by 3 components, which I can summarize like this. So this one here is the unit matrix in 3 dimensions, this as well. And this factor t minus t prime has to be multiplied with the unit matrix in 3 dimensions. This is shorthand notation. What I want to emphasize here is that we can write this Green's function in exactly the same way on an expanding background in cosmology if we take the growth factor for linear density fluctuations d plus as a time coordinate, and then this Green's function implements the Seldovich approximation. So in other words, we choose here the Green's function in such a way that the motion, the inertial motion, in the Seldovich time t is used as a reference motion. And then of course we have to adapt the interaction potential such that it will act relative to that particular reference motion. And this means we have to replace the interaction potential small phi, or the gradient of the interaction potential small phi, by the gradient of an interaction potential large phi, minus a correction, and this correction is m dot over m, and here I'm referring to the time-dependent mass that we get because we transform the static background, the expanding background to the co-moving coordinates. Now we get an integral 0 to t over dt prime m times the gradient of phi, and this has to be taken at t prime. So, in other words, we use the Seldowich approximation as a reference motion, and then of course we have to adapt the force that is acting on the particles to that particular reference motion. And this means that the potential capital phi here has to satisfy the Poisson equation, some amplitude a phi, times the density contrast delta minus the linear density contrast delta linear. Alright, so let me summarize again. We choose the Green's function such that the inertial motion of particles in the Seldowich time is used as a reference motion. Then, of course, we have to adapt the interaction potential or the interaction force between the particles in such a way that it acts on these reference trajectories rather than on inertial trajectories in the cosmological time. And then we have to correct the force in this way. We have to introduce a new interaction potential capital phi, and this new interaction potential capital phi satisfies the Poisson equation that is given here. And this is interesting because you see that on the right hand side only the difference of the actual density contrast and the linear density contrast enter. And this reflects the fact that, as is well known, in the Seldowich approximation, large-scale gravity is already included in the inertial motion by choice of the Seldowich time. And the Seldowich trajectories are preferred to any other trajectories by the fact that initially, so near time equals 0, there's no force acting on these particles. And this concludes step number 2. Right? Step number 1 was the solution of the particle for the Hamiltonian equations of describing the particle trajectories through phase space. Step number 2 was the particular choice of the Green's function that we use for k of t. So far, so good. Now we come to step number 3. And step number 3 is the construction of the generating functional of k of t. Now, what do I mean by that? First of all, I write down with p of x. And again, this is somewhat shorthand notation because I mean the phase space coordinate x at a time t. I write down with p of x the probability to find a particle at time t at phase space position x. And I can write this as the transition probability from some initial state xi to the final state x times the probability for the particle to be at phase space position xi initially, integrated, this is not a nice integral sign, integrated over all initial phase space positions. Now I call this the integral measure d gamma, just to introduce shorthand notation here. And since I have to do with classical particles here, this transition probability can be written as a delta distribution here of x minus x bar. Right? And with x bar, I mean the solution of the Hamiltonian equations as a function of time, starting at phase space position xi. Now, since x and x bar are functions of time, this is a functional delta distribution. And this is because we have classical particles. This is an important part of the construction of KFT here. All right, now, beginning with this probability for a particle to end up at position x in phase space, we construct the generating functional as a function of a source field J, which we get as usual in the following way. We integrate, in whatever way, the probability to find a particle at phase space position x after time t, and we multiply this with an exponential containing a scalar product of the generator field or the source field J with the phase space position x. Now, we have to integrate over all possible trajectories leading through phase space from the initial state xi to the final state x. So we have to integrate over functions, and therefore this is a functional or path integral. This scalar product up here has multiple components. It contains an integration over time, which I would not go into detail here. And the factor I here just appears for similarity with the approach to statistical quantum field theory and has no further importance or no further significance here. Now, if you imagine inserting this expression for p of x into this path integral for the generating functional, you see that the delta distribution will pick out x bar from all possibilities x in the scalar product, and what remains will just be the regular integral over initial states times the phase factor e to the power of I j x bar. And this is the generating functional of k of t. Let me write this down. Generating functional of k of t. Now, of course, we can proceed with this generating functional in the same way as we proceed with generating functionals in statistical quantum field theories, for example, or other statistical theories. In other words, we can take functional derivatives with respect to the source field J in order to derive statistical properties of the particle distribution in phase space. Before we come to that, let me introduce in the fourth step the concept of a density operator. All right, so we come to step number 4, and I promised we will go up to step number 6, so we have already one half of the steps behind us. Well, in step number 4, we will introduce density operators, and we will deal with them. So I start with the density in configuration space rho of q. And since I have to solve the density field into particles, we have to sum over all particles their delta distributions to the density. So the sum over Dirac delta distributions of q minus qi over all particles I is going to be the density. I'm going to replace the individual contributions by their Fourier representation. So this is why I wrote an f down like this, curly f down here. And in Fourier space, the delta distributions will turn into e to the minus I k times qi. Right, this is now the density in Fourier space for a wave vector k. All right. Now we have a particle position in here, the particle position qi. And by construction of our generating functional, we can replace this particle position qi here by a functional derivative with respect to the corresponding source field. So we go over from this sum over Fourier phases to an operator expression for it. And in this operator expression, what I do is I replace the particle position qi by a derivative with respect to the q component of the source field j for particle I. And of course, in order to cancel the factor I, which is being taken down from the e to the I j x bar expression in the generating function, I have to multiply this with a factor of minus I. All right, so I replace the qi by this expression here. And then you see that all that remains is a sum over exponential of minus k times the derivative with respect to qij. So now I have an expression that with which I can act like with an operator on the generating function, and therefore call this a density operator for wave vector k. All right, this is very interesting because derivatives generate translations. So an exponential of a derivative generates a finite translation. So the effect of this density operator will be that it will translate the source field j in the generating functional by a vector L, which we will have to specify. But keep in mind that the effect of this density operator is going to be a shift of the source field j by an amount L. All right, now we apply R of these density operators to the generating functional. And when we are done, we replace the generator field by 0. And by construction of this generating functional, this will be the average for the density fields rho tilde 1 to rho tilde r in Fourier space. So this is going to be a polyspectrum, an rth order spectrum for the density fluctuation. In other words, if I set r equals 2, then I will get a power spectrum from the generating functional. Now, the combined action of these R density operators will be to replace the generator field J by a translated field J plus L. And if I now take this at J equals 0, this means that the generator field J will just be replaced by the translation vector L, which, according to this definition of the density operators, will be the sum over all k vectors, which are related to these density operators rho 1 to rho r. So this function extends from j equals 1 to r. Each of these density operators rho 1 to rho r brings its own wave vector k1 to kr, and the effect of applying all of these density operators to the generating function is that they will create a translation L, or a shift L, of the source field. which is given by the negative sum over all these k vectors. This is a shorthand notation, but it shows you the principle. And so this means that if we apply all of these density operators to the generating functional and evaluate the result at j equals 0, this will just be the generating functional now at source field L rather than source field J. All right, this has been the fourth step. Now we are going to come to the step number 5. And in this step, I will introduce what we call the mean field approximation. So we are aiming at calculating power spectra. In other words, I need to apply two density operators for K1 and K2 to the generating functional set of J. I will have to take this at j equals 0. I will get set of L. And according to what we wrote before, this is the integral over the initial phase space times e to the power of I L x bar. But x bar, if you remember, was the Green's function of t and 0 applied to the initial phase space position minus the integral over the Green's function times the vector 0 gradient phi integrated over dt prime from 0 to t. So I call the first part here, which is the free motion, the inertial motion in the Seldovich time coordinate, I call this x bar 0. And this part here, which contains the gravitational interaction of a given particle with all other particles, I call this y. So then I can write the generating functional at the shift vector L, which will be the power spectrum, as an integral over d gamma e to the power of I times L x0. This is the free motion, minus I L y. This contains the interaction. All right, and now the essential step of the mean field approximation is the following. I take the gradient of phi and I replace this by an average value of the gradient of phi. And what I mean with that is that for all particle pairs that I can identify in my particle ensemble, I will have a separation vector q, and the gradient of the interaction potential will have to be taken at the absolute value of this separation q. Now I can calculate an average by integrating the gradient of phi at the separation q with the probability of finding two particles at separation q. Now this probability has a Poisson contribution, a random contribution, which will not contribute because it will average out, and it will contain a correlated contribution quantified by the correlation function psi of q. And if I integrate this over all q, I get an average of the gradient of the interaction potential averaged over the correlation function of particles. All right. This is a product of two functions. And if I go to Fourier space, so here's the f again. If I go to Fourier space, this is going to turn into a convolution of the Fourier transform of the correlation function, which is the power spectrum, and the Fourier transform of the gradient of the potential, which is I k phi tilde where phi tilde is the Fourier transform of the particle interaction potential. And this is going to depend on the wave number k. And this is what we call the mean field approximation in the KFT context. So then we can replace this phase factor here minus I L times Y in the mean field approximation by the scalar product of L with the integral over the Green's function, which we know. And now we insert here 0 and P delta convolved with K phi tilde. And we integrate this over dt prime. All right. So first of all, you see the I factors, the imaginary factors, cancel out. And we call the result of this the mean interaction term Si, which will depend on the wave number k. All right, and finally, in step number 6, we come to the power spectrum in mean field approximation. Power spectrum in mean field approximation. So I told you before that the set of L, the generating functional taken at the shift vector L, if we have applied two density operators, is the nonlinear power spectrum of the density contrast as a function of k. Now I'm going to rewrite the generating functional again, but I now take into account that we have averaged the interaction part. And because we have averaged it, we can pull it out of the integral that remains in the generating functional. So we get an exponential interaction, mean interaction term, which is now being applied to the integral over d gamma, e to the power of I shift vector L times the inertial motion x0. Now this we call the free generating functional, z0 taken at L, or the nonlinear free power spectrum for which we use this curly p here. All right, so we get a relation for the nonlinear power spectrum, which we can write as interaction term raised to the e power applied to the free nonlinear density power spectrum. All right, this concludes my introduction to KFT in 6 steps. And now I will return to the presentation on slides. So this is how far we've got now. Let me proceed here and see whether I'm overlapping with this. No, I'm not. All right, so this is the main result we have obtained in the mean field approximation. We have obtained a closed expression for the nonlinear density fluctuation power spectrum in this mean field approximation by suitably averaging the interaction term between the particles. And you've seen that this averaging is quite natural. We average the interaction potential weighted by the correlation function between particles. And we have to apply this to the free nonlinear power spectrum, which of course you can calculate in the Seldovich approximation. Now let me proceed to the result. And I think I will have to hide a bit here so as not to overlap with this. All right, let me put myself over here. Alright, so what you see here is the result of this mean field approximation and of calculating the nonlinear power spectrum in the mean field approximation. As a function of wave number from 10 to the minus 2 to 10, you see here compared the linear power spectrum evolved to redshift 0, that's the dashed blue line, that's the Bardeen power spectrum. You see the numerical results as given, for example, by adapted halo model, by the adapted halo model. This is the dark red curve, this is our reference. And in light red, you see our analytic result in the mean field approximation of KFT. And you see in the bottom panel that the agreement between the analytic result and the numerical result is quite good. It's for almost the complete K range here, better than approximately 5%. If we would go to larger wave numbers K here, we would of course get more deviation, which would show a limitation of the mean field approximation, which we are planning to overcome with a more rigorous derivation as I've shown here. I should emphasize that the derivation contains two parameters which can be calibrated from within kinetic field theory itself. So the theory has essentially no free parameters, but you can use these two parameters and change them by a small amount in order to improve the agreement or in order to optimize the agreement with the numerical results. And this leads to an approximately 10% adaptation of these parameters compared to the calibration of the parameters within KFT itself. So this is one important result. Now let me come to another class of results which I believe will turn out to be important very quickly. We have studied the asymptotic behavior of the free nonlinear power spectrum, curly P of K, and found that, quite irrespective of the initial conditions, this asymptotic behavior for large wave numbers K is given by K to the minus 3, and the 3 is exclusively set by the number of space dimensions. And this is irrespective whether we start with a cold dark matter power spectrum or a hot dark matter power spectrum or even a power spectrum that looks like a delta function. So this is a very important result, which has been shown under a more restrictive context already by Pietroni and a co-author. And we have confirmed this here for a very wide class of initial power spectra and initial conditions. If we return to the mean field approximation to the nonlinear power spectrum, this means that we can now calculate the asymptotic behavior for very small scales, for very large wave numbers K, in the mean field approximation. And it seems that in this way we can approach the question why gravitationally bound structures in the universe attain a universal density profile. Likewise, we could show that the free bispectrum behaves asymptotically like K to the minus 11 halves, K to the minus 5.5. Now let me show you these results. So here you see the asymptotic behavior of the free nonlinear power spectrum for very large wave numbers. This is taken from the PhD thesis of Sarah Conrad, and publications are on the way. You see different curves here because for the integrals that enter into this asymptotic description, we have to cut off the cold dark matter power spectrum at some very large wave number, Ks, as you see here. So this image, or this figure, shows you that this asymptotic behavior is quite independent of the cutoff chosen to the cutoff applied to the cold dark matter power spectrum. Only the amplitude changes, but not the slope of the asymptotic tail of the free nonlinear power spectrum. All right, let me proceed to the bispectrum. This is taken from the master thesis of Ricardo Weibel. The publication is in preparation. And this shows you that quite irrespective of the initial slope of the linear density fluctuation power spectrum, right? A slope of 0.5, 1.5 or 2, at late times, the free nonlinear bispectrum develops this asymptotic behavior of k to the minus 5.5 and not k to the minus 6 as has often been claimed. Let me come to other applications. With kinetic field theory, you can not only describe dark matter, but you can also describe mixtures of gas and dark matter. And one result that we have obtained for such a mixture is shown in this graph. You see here in red the acoustic oscillations that form by the gravitational drive of the cold dark matter fluctuations on the baryons. You see in orange the superposition or the power spectrum for density fluctuations in a mixture of dark matter and gas, whereas the silk damping has been neglected so far. And this is why you see the fluctuations to arbitrarily large wave numbers as shown here. And with the slight shift for clarity, you see in blue superposed the power spectrum, including baryonic acoustic oscillations. And you see that with KFT for mixtures of gas and dark matter, the wavelength and the amplitude and the phase of the baryonic acoustic oscillations are reproduced. And if we would include silk damping as well, then the amplitude of the fluctuations along the orange line would decrease as seen in the blue line above. Another interesting result has to do with the application of kinetic field theory to alternative theories of gravity. Since we can expect that in alternative theories of gravity, the nonlinear density fluctuation power spectrum will be very close to what you expect in general relativity, we can describe changes in the nonlinear density fluctuation power spectrum by a functional Taylor expansion with respect to the two functions that enter into this description, namely the cosmological expansion function E of x, which is essentially the Hubble function, and possibly a change in the gravitational coupling strength, which of course in general relativity is just Newton's constant, but it changes to a functional dependence in some alternative theories of gravity. And if we apply this functional Taylor expansion to the nonlinear power spectrum, we find a very generic behavior, which we illustrate here with one particular modification of gravity, the so-called generalized Broca theories, which are based on a vectorial extension, or the extension of the theory of gravity with a vector field. So you see here the relative change of the nonlinear density fluctuation power spectrum compared to the result in the standard cosmological model. And you see that you expect a very generic behavior on small scales where the power changes on the order of a few percent. All right, let me come to the summary. I've shown you the principle of kinetic field theory for structural formation, which is a kinetic or statistical theory for classical particle ensembles in and out of equilibrium, which is constructed in such a way that it avoids the shell crossing problem. It provides a systematic approach to perturbation theory, but it also allows a mean field approximation, which is very successful in describing the nonlinear evolved density fluctuation power spectrum. Also very interesting are the asymptotic results on small scales, which lead to an asymptotic behavior of the nonlinear power spectrum like k to the minus 3 and of the bispectrum like k to the minus 5.5. I've shown the results which we have obtained by applying KFT to mixtures of gas and dark matter. And we have also applied KFT to extensions of the theory of gravity, or generalizations of the theory of gravity. With this, I would like to conclude, and I thank you very much for your attention. I've listed here a number of references, and I'm looking forward to the discussion. Thank you very much.